Hello. In this video, we're going to talk about probability distributions. In chapter one, we dealt with what we called variables that were either qualitative or quantitative. Now we're going to really just deal with quantitative variables. And in algebra class, numerically, we would label a value x depending on kind of one of the particular outcomes. But every time we had an equation, something like 2x equals 4, that value of x was determined every time. That was a deterministic variable. And what we might want to do now is have more probabilistic means. So, for example, if we toss a die and we let x be the number observed on the upper face, there really is no equation that we can set up. The outcome of x will change depending on the outcome of the experiment, right? So the value of x might be 1, might be 2, or so on. And each of those possible outcomes are linked to a likelihood that that kind of top face is going to show. And the key here is this is not a deterministic variable. And so we need a new term. A variable x is what we call a random variable, provided the value it assumes that kind of corresponds to the outcome of an experiment, but the value it has is given by chance or some random event. And so just two kind of quick examples might be x, the number of defects on a randomly selected piece of furniture in a manufacturer, or it might be the average SAT score for a selected student, right? Each of these is not always going to be the same number, right? Two different people are going to score differently on the SATs. Two different pieces of furniture coming off of a line might have two different number of defects on them. And so each of these random variables can either be discrete or continuous, depending on the values that x can assume. And for chapter 5, we're really going to refer to just discrete random variables, things that we can count. When we introduce the normal distribution in chapter 6 and so on, that's when we'll talk about continuous random variables. But in any event, what we need to know are two things. We need two pieces of information when we really speak about any type of random variable x. First, we need to know the values that x can assume, right? What can I know? What are my outcomes? What are my possible outcomes? And two, what are the corresponding probabilities of each outcome? So, for example, if we're going to talk about uh, that kind of first example up here, if we're going to roll a die, I want to know what the possible outcomes are for rolling a die and what the probability or the likelihood of each of those outcomes is. And the idea that takes both of these things together is what we call a probability distribution. A probability distribution for a discrete random variable is going to either be a formula, table, or graph. We're really going to rely on formulas and tables. That will give the possible values of x. So a probability distribution will give us these two pieces of information. It will give us the outcomes for x and the corresponding probability, which we'll call p of x, that is associated with each value of x. One of the important things about probability distributions is these values of x are going to represent mutually exclusive numerical events, right? We can't have the outcome of 1 and 2 occurring at the same time. So each of these x's will be mutually exclusive. And because of this, we get some facts about probability distributions. The requirements or facts of a probability distribution are that each of the probabilities of my outcomes x fall between 0 and 1, and the sum of all of the probabilities for the different outcomes has to equal 1. So let's look at an example of building a probability distribution. So a coin is tossed in the air 3 times, and we're going to let x equal the number of heads observed, and we're going to find the probability distribution for x. And so we're going to build this kind of from the ground up. And so the way we're going to do this first is by looking at, well, what are the different possible values of x? If I'm going to flip a coin 3 times, one of the outcomes is I could have 0 heads. I could have 1 head, I could have 2 heads or 3 heads, right? Those are all of the possible outcomes. And so what we want is the probability for these types of outcomes. And so we don't have really any shortcuts or any rules. So right now we're going to have to list all of the simple events that could happen for each of these outcomes. So what are all of the ways that we could have 0 heads when we look at flipping a coin 3 times? That is only the outcome of tails, tails, tails. Right? What are all the outcomes we could have for flipping a coin 1 time or 3 times and getting 1 heads? That's heads, tails, 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 heads, tails, and tails, tails, heads. What are all the ways we could flip a coin 3 times and observe 2 heads? That's heads, heads, tails, heads, tails, heads, and tails, heads, heads. And finally, what's the only way we could flip a coin 3 times and observe 3 heads? It's heads, heads, heads. And when we did our discussion of probability, we said all of these are simple events. They're all equally likely. And to find the probability, all we're going to do is count how many things are in each category, right? There are a total of 8 outcomes. So the probability of getting 0 heads is going to be 1/8 because there's 1 outcome out of the 8. The probability of seeing 1 heads will be 3 out of the 8, or 3/8. Likewise, 3/8 and 1/8. The way we can represent that a little bit more cohesively is, again, by a table. So we'll let one horizontal axis be the outcomes, 0, 1, 2, and 3, and the other horizontal axis be its corresponding probability. So 1/8, 3/8, 3/8, and 1/8, right? This is how we will build a probability distribution. We won't build a lot of them like this, right? Eventually, we will learn a shortcut. In the next section, we will learn a shortcut for coming up with the number of outcomes and, more importantly, finding their corresponding probabilities. And that is really going to be the difficult part, but that's where we're going to get the most help from this. One fact about probability distributions is they act very similar to the samples and populations we studied in chapters 1 and 2, and therefore can have parameters or statistics. For example, mean and variance. So if we let X be a discrete random variable with a given probability distribution, we can say the mean, or a word we use for distributions is called expected value of X, is still given by mu, right? That was the variable we used for mean, or kind of the grown-up one we use as e of X. That's the expected value of X. And that is going to be the sum of my outcomes times their corresponding probabilities. So the sum of X times their corresponding P of X's. If I want to look at the variance, I still can look at a discrete random variable X with a given probability distribution, and this time we need a mean. The variance, sigma squared, is going to be the sum of my x's times my, or minus my mu squared times the P of X. It is very similar to what we did with variance and mean in the previous chapters, but here we're dealing with a probability distribution, so there's no need for division now. We can multiply each of these outcomes minus the mean squared by the corresponding probabilities of those outcomes. And of course, we still might want to know the standard deviation. This, again, I like this to be kind of a variance forward class. Otherwise, we would put a square root in front of everything. That would be very ugly. So we can just say the standard deviation, again, which we just represent by the Greek letter sigma, is just going to be the positive square root of its variance. We do have an alternative form for variance. It is sometimes preferred. We can compute the variance sigma squared, and the way we would talk about this is e of x squared minus e of x quantity squared, or as a formula to be just the sum of x squared p of x, and then at the end of that sum, we subtract mu squared. I tend to prefer this. It is less subtractions, right? In this way, we're taking every data point and subtracting it from the mean and then squaring it. Here, for an equivalent notation, all we need to do is do one subtraction at the end. So let's do an example of finding mean or expected value and then variance. So let's say an electronics store sells a particular model of a laptop, and there are 4 laptops in stock. Let X be the daily demand for the laptop at this store with a probability distribution below. So the demand for 0 laptops sold is going to be 0.1, for 1 laptop sold is going to be 0.4, and so on. And we want to find the mean, variance, and standard deviation of this random variable X. So for the mean, or E of X, right, what we're going to do is take the sum of our X times the P of X's. So that's going to be the first outcome 0 times its corresponding probability of 0.1, plus 1 times its corresponding probability, likewise, plus 3 times 0.15, plus 4 times 0.1, plus 5 times 0.05. And if we do that, we're going to get 1.9. If we add all those up, multiply them and add them up, we get the mean, right? A pretty straightforward, right? We don't need to divide by 6 the total number of outcomes there are. That division, so to speak, is really taken up by the fact that we have a probability distribution, that for every outcome, there is a corresponding likelihood. So by the pure fact that we're multiplying each of these outcomes by a probability, that means we don't have to divide anymore, right? So this is going to be the mean or the expected daily demand for laptops in the store. And so, for example, if the store only has 4 laptops, we are pretty certain that the store will be able to meet the demand, that it's very unlikely that in a given day, someone's going to want 4 or more laptops, right? Let's look at finding the variance. Variance is sigma squared, right? I tend to like to do variance being the sum of X squared times P of X minus the mean squared. So the formula is going to look very familiar or very similar to what we just did. It's going to be the data point squared times its probability. 1 squared times its probability, plus 2 squared times its probability, plus 3 squared times its probability, 0.15, and so on. Plus 5 squared times its probability. And then from that, I'm going to subtract 1.9 quantity squared. So instead of having a lot of mean minus or data point minus the mean squared, I just have to subtract that once. And so if I do that, I'm going to get 0.54 minus, again, 1.9 quantity squared, and I'm going to get 1.79 if I round that to 2 decimal places, right? That is just my variance. If I want to find my standard deviation, that's the easiest calculation we'll do. That is the square root of my variance with a square root of 1.79. If you do that, I get 1.34, rounding it to 2 decimal places. So my 3 parameters here, the expected value is 1.9, the variance is 1.79, and my standard deviation is 1.34. All right, let's do one more example where we will actually kind of build the probability distribution. Let's say we're being involved with a lottery that benefits a local charity. They're going to sell 8,000 tickets at $10 a ticket with a grand prize of $25,000 car. Let's say you purchase 4 tickets. What is your expected gain? And anytime we see the word expected in a problem like this, we can think that is going to be expected value or mean again. Right? What we don't have in this case is a distribution. So we will have to build a distribution. I'm going to need outcomes and their corresponding probabilities. But in this case, that is okay because there are 2 main outcomes when we deal with gambling or we deal with lotteries like this. you're either going to win the lottery and get a prize, or you're going to lose the lottery, right? If you win the lottery, what is your outcome, right? Winning the lottery, your outcome is winning the $25,000 car. However, whenever you do these kind of gambling or lottery examples, this outcome is really your net win. We're looking at our net win because every time you gamble or participate in a lottery, you have to pay money, in this case, $10 per ticket for 4 tickets just to be entered into this. So your actual winning outcome is not 25,000, but 25,000 minus 40. Your other outcome, what happens if you lose? Well, if you lose, you don't get anything, but you lose your $40. So it's just minus 40 for losing. And let's look at the probability. What is the probability that you win this lottery? Purchased 4 out of the 8,000 tickets. So the probability you win is 4 over 8,000. And then the probability you lose is going to be 7,996 out of 8,000, right? So your expected value, E of X, is just going to be, again, the sum of my outcomes times my probabilities. And in this case, your first outcome is going to be 24,960 times the probability that you win the, plus your second outcome, which is minus 40, right? That's what's going to happen if you lose, times not 7,996 over 8,000, right? The probability that you lose. And if you compute this, you're going to get negative, since this is money, $27.50. That is your expected gain, is negative $27.50. And so in this case, the problem is over, right? That's what we are asking. But what you may be wondering is, how could we get a value that is not even close to one of the possible outcomes? And again, we have to think about expected value as not just one of the possible outcomes. But again, we've mentioned that the power of language in mathematics, that sometimes the mathematical definition of a word is not our connotation of the word. So the word expected is not what can I actually expect to see in a real world example. Expected value in mathematical context really is closer to a mean. What is likely to happen? And so when we see an expected value of a gambling game being negative, what that tells us is, over the long trends of this, we can expect to lose money more than we will win money. Even though we stand to win almost $25,000, the likelihood of winning that money is so low that if we play this game over and over and over again, we can expect to kind of always lose this type of gambling. All right, so that's just kind of a quick explanation of what that means, and not to fear if our expected value is actually not even close to one of the outcomes. That's actually going to happen more often than not. Right? If you have any questions, let me know. If not, I'll talk to you next time.